All right, so we have a rod here with this mass, and initially it rests pivoted at one end, so it's able to rotate with negligible friction. Suppose the disc in the figure has a mass, so we have a pivot here, strikes and sticks to the rod. The disc's dimensions are small enough that may be treated as point mass. The rotational inertia is this. Which of the following quantities must be the same for the disc rod system before and after the collision? Okay, so now what we have to think about is even though they collide, we think about the system, there's an external force from the pivot, from the nail that's holding it in place. And that prevents this rod from actually moving, right? Like you can't just go to I can't slam it and we'll prevent it from moving. So there is an external force. The external force is definitely not zero, which means that the linear momentum might not be conserved because the impulse is the change in momentum and this is non-zero, then the change in momentum is non-zero. In a collision, we don't know kinetic energy is conserved in terms of this must part, right? Only if it's an elastic collision. That only if they tell you and there's no physical damage. But in this case, because it sticks, there's definitely physical damage. Angular momentum. Well, if we're rotating around this axis point right here, even though the external force isn't zero, the net torque is zero. There's no external torque on the system, which implies that the torque over time, the angular impulse, is zero. So there's no change in angular momentum. That's why that is conserved. Okay. What is the angular velocity of the two objects after the collision? All right. So now the angular, it's the same as the angular momentum. The angular momentum is equal to the angular momentum after. So let's look at initially, this thing has no angular velocity. And then this thing has an angular velocity, which is mvr. And r refers to this distance here. So this is 1.2 meters. And then the v0 is 30. And then we know the mass is, so we know the initial angular momentum. So the rod doesn't have initial angular momentum, but the clay does. And the initial angular momentum is mvr, which is 0.05 times its velocity, perpendicular to this r vector, times the r being 1.2. So this is the initial angular momentum. 0.05 times 30 times 1.2. And that's 1.8. Now afterwards, they both stick together and they're moving with an angular velocity, right? So that equals I omega. Now I need to know what the I of the whole system is. Well, the rod is 1/3 ml squared. But remember, we've got to think about the whole system. Because we had to include both objects in the system because they do exert forces on each other. And I don't want to include them. So I've included both objects in the system. Okay. And then we want to do the clay mass is kind of a mr squared situation going on. So if we look at that, that's going to be 1/3 mass, which is 2 times L squared 1.2 squared, plus the mass of the clay times its distance, which is at the very end, 1.2, times omega. And that has to equal 1.8. So you just compute that and divide the 1.8 to get the angular speed at this point. Okay, so we're going to do 1/3 times 2 times 1.2 squared plus 0.05 times 1.2 squared. That's and then 1.8 divided by that, and I get 1.74 radians per second. See, what's the kinetic energy of the two objects before and after the collisions? Well, before, this guy just has some linear, kinetic energy. It's just 1/2 mv squared. And it's just this guy that's moving. So he's 0.05 times 30 squared. So this is how much kinetic energy he's got. 22.5 joules. And then afterwards, what is the kinetic energy? Well, now they're both moving together, rotating around the axis. And the I is the 1/3 times 2 times 1.2 squared, plus 0.05 times 1.2 squared, times the 1.74 squared, right? So 0.5 times this, I get 0.90 joules. Okay, so we lost a lot of energy. Definitely energy was not conserved, right? That's what we see in part A. Okay, what is the angular impulse exerted by the disc on the rod about the hinge? So now we're not talking about, we're talking about not keeping them as a system, because we want to know how much impulse. So we want to think about oops, this was C. Yeah, this was C. So D is angular impulses. We want to just talk about the rod here, right? Now the rod doesn't have any angular momentum to start with. So we want to just know the torque and the change in time. We just want to know what the angular impulse is. But we just know if we know the final angular momentum of the rod, right? That would be sufficient. So what is the angular momentum of the rod? Well, it's I omega, and the I of the rod. Now we're just talking about just the rod. Okay, so we're not going to add in the clay because that's not part of our system anymore. We only care about the rod part. And then we're just going to do this. Because we know how fast it's going. We know it's rotational inertia. And we're just going to multiply those things. Oops. 1 divided by 3 times 2 times 1.2 squared times 1.74. And I end up with 1.67 Newton meter seconds. I don't remember. Yeah. Or you can use kilogram meters squared per second, whichever unit you want. Okay.